Hello class, and welcome to our last kind of unit in the course. I want to mention that although I say last unit, we're going to combine unit 7 and 8 together. Okay? And the reason why we're combining those two together is because we're now going to shift in our course and we're going to deal with what's called discrete functions. Okay, so with discrete functions, that means when we draw a graph, ladies and gentlemen, we're not drawing a smooth curve like a sinusoidal or a smooth exponential or a smooth quadratic or reciprocal or square root. Basically, when we're doing a graph, we're looking at a trend where we cannot connect the dots. So that's why we call it discrete. Okay, just think about continuous functions have been every function we've done so far. Now we're developing or taking a look at getting into what's called discrete functions. Okay, the best way I can relate this to you and where you're going to use this in real life is whenever you do any banking. We're going to be taking a look at how interest is earned or how you have to owe interest if you borrow money. It's going to be important to you guys if you're going through to school, post-secondary, if you need to get OSAP, you need to know when to pay things back and whatnot. So this is very helpful, and this relates to the real world. Okay? So again, our last unit test will be combined with unit 7 and 8 together, and the reason we combine them is because 7 and 8 deal with both discrete functions. Okay, so before we get right into what a sequence or what discrete functions are, we've got to get into some terminology. So today we're going to deal with what's called sequences. Okay, so taking a look here, ladies and gentlemen, a sequence is an ordered list of numbers. Okay, and I want you to write down here that it has commas. And you can see some examples below. Okay. Now we're going to specify into a special type of sequence, which is called an arithmetic sequence. Next day, we'll also take a look at a geometric sequence, so you have to make sure you know the difference between the two of them. Okay? So an arithmetic sequence has what we call a common difference between the consecutive numbers. So watch how I do this, ladies and gentlemen. Okay, what happens between going from 2 to 4? Well, hey, you add 2. What happens between when you go from 4 to 6? Again, you add 2. And what's the patterning here? You probably have done this in elementary school, but we just haven't called it a common difference. Okay? So in this case, the common difference, D, equals 2. So the common difference, ladies and gentlemen, is represented by the symbol D. Okay? So that deals with the common difference, and I'll just use DIF for short form. Another letter that's going to become important for you to know is what's called A. And A is always going to be your first term in a list of values. So A, in this case, equals 2, and this is because this is the first term. Okay? Take a look at our second example, ladies and gentlemen. Let's find the patterning. What's happening in each case? Okay, so we're following our pattern, and notice in each case that we're adding 4. So what does that tell us? The common difference is 4. D equals 4. If you have hard values, ladies and gentlemen, you can't tell. You take the last one, so 15, and you subtract the one before it. So that would equal 4. Or you can take 11, subtract 7, that equals 4. Okay, so for really hard examples, if you can't see the trend or if you've got decimals in it, you just take you know, when you take a look at a first differences on a table of values, right? You always take the lower and subtract the upper. So think about that. You take the right digit and subtract the left digit. Right digit, subtract the left digit, etc. Okay, so that's how you get that. All right, I'm just going to erase this because I'm still going to need this space. All right. Now, the next thing I also want to do is point out that, hey, in this, folks, A, in this case, our first term in our pattern is 3. Okay. All right, moving on. Last example. What's happening each time here? Well, you should notice that as you go from 12 to 9, it's getting smaller, so it's going to be less. So we're going to be subtracting 3, subtracting 3, subtracting 3. So in this case, D equals -3, which again is your common difference. And looking at our start value, ladies and gentlemen, A equals 12. If we know the common difference and the first term, which is A, we can sub it into a formula that you're going to see down here below. Okay, so that's why I'm introducing A and D already. But let's just take a second and go in our textbook to page 416. And we'll take a look at AB. You can pause the video now if you need to go get your textbook. So run and get it. Okay, hopefully you've got it now. And taking a look on 416, the first thing you'll note, ladies and gentlemen, this is a good page to note to bookmark because it's got a lot of definitions on it, okay? So if you're ever wondering what definitions you're going to need, look at page 416. But we're going to take a look at the investigation with math. It says, Chris is using linking cubes to create different shapes. The first three shapes are here shown below. He wrote a sequence that represents the number in each shape. So, taking a look for A, it says to create the first three terms in his sequence, okay? So in figure 1, how many cubes does he use? He uses 1. Put a comma. In his figure 2, how many cubes does he use? You're going to have 3. Okay? And in figure 3, if you count the cubes, you're going to see that he uses 7. I'm sure you remember doing this in elementary or in science. Okay? So it says to give that. And we could keep going, right, guys? We could say, hey, next, what's happening? Okay. Well, what is happening in each case? Let's take a look at our first three diagrams. What's happening in each case, guys? Hopefully you see the pattern that we're adding to each time. So I could extend this if I wanted to put 7 and add 2 more, to put 9, add 2 more, to put 11. And I'm going to go dot, dot, dot because that pattern keeps on going. And how do we know to keep the pattern going? Because we know the common difference, D, equals 2. All right. And it says, how is each term in this recursive sequence related to the previous term? How is it related, ladies and gentlemen? Okay, it's related because the common difference is 2. So each time, for example, recursive means the one before it. So what's happening here? Okay, so if I've got 7, what happens to get to 9? Hey, you have to add 2. All right. So based on that, ladies and gentlemen, we can find any term number we want. And if you're wondering how we identify term numbers, okay, the first one is whatever you see first. So in this case, up above here, 1 is my first term, 3 is my second term, 5 is my third term, etc. Okay, so I could even follow it up to the 100th term if I wanted to, and you can sub things in to find that. Keep that textbook page open because we're going to be using more of it, ladies and gentlemen. But let's just write down our general term for the arithmetic sequence. And what it has to do with, guys, it says any term. So let's, for example, say we want to find the 100th term in this sequence. Okay, if we want to find the 100th term, what we're going to do with our above example, we're going to go t at 100. Equals A, what's our first value, guys? 1, plus my nth number, which is 100, subtract 1, times D, which is my common difference, which is 2. So we can simplify this. If I have some more room here, I would say 1 plus, what is, ladies and gentlemen, 100 minus 1 is 99. 99 times 2 is 198. So if we asked and said, hey, what value, if we took 100 terms, what value is going to be in the 100th term? You would have 199 cubes there. Okay? You can set it to any value. Okay? I just made up an example here of finding, hey, in the 100th figure. So in that diagram on the page 416, if we went all the way to figure 100, how many cubes would be in that figure? All right, so just make sure, guys, when you're taking a look at the general formula, T at n tells us any term, we can sub in for n, okay? And the three things we need to remember are that A is the first term, and that's going to be similar through the formulas we're going to learn in the next couple days. D is a common difference, and that's only used when we have what we call arithmetic patterns. And n is the term number, and that'll be consistent in all units, or in all formulas. Okay? So for the general term, we replace a and d with the numbers, but not n. Okay? In this case, I actually subbed it in and found the values, but you can just sub it in without. Okay? So taking a look, let's refer back to that example on page 416. Okay? It now says for D, determine the formula for the general term. So what do we know so far? We know that A equals 1, and we know that D equals 2. So if I write out my general term, I sub in what I know. So right now I leave n as n because I don't know what term number I'm doing. So it's going to be 1 plus n minus 1 times 2. Remember, ladies and gentlemen, that this is a distributive law, but it goes backwards. Okay? So I simplify 2, or getting there. 2n equals 1 plus 2n minus 2. And collecting like terms, ladies and gentlemen, I will find out that, when I collect like terms, I've got t at n equaling 2n minus 1, just putting it in proper order. Okay, so that's D. Okay. And E, ladies and gentlemen, says calculate the general term use the general term to calculate the 100th term. Well, I've already done it up there, but I'll just show it again. So what do we know now? Based on our general term, which is above, we now have given that, hey, from the 100th figure, or the 100th term, okay, so we sub that in, so t at 100 equals 2 times 100 minus 1, and that's going to equal 199. All right, so it tells us that if we are at figure 100, there's 199 cubes in that diagram. All right, now we're going to deal with what's called a recursive sequence, okay? And the last one in the term is given by each successive term is determined by its previous term. So basically, if we take a look at page 416, number H, we're going to be doing this together. Okay, so the recursive formula tells us that t at 1 equals 1. So that means the first term is 1. And in our sequence, the second term was 5. And the third term, was 3, and then my third term was 5. Okay, remembering that t1 equals a, so that's your first term. Okay, so what do we know with that, ladies and gentlemen? We know that we can take that and plug that into this formula as well. Okay, so if you're trying to figure out over here what the fourth term would be, you've got to take the third term and then say, hey, how do we get to the fourth term? You have to add d. So it's going to be 5 plus 2 to equal 7. Okay? So that's if you're trying to find the fourth term. But if you're trying to find the general term, ladies and gentlemen, you take a look at the term in front of you. So t at n equals t at n minus 1, so the term before you, and then you add d. So I'm just following this one right here. You add d. In our case, d is 2. Okay? So that's the terminology, or that's what we call the recursive sequence formula to help you find certain patterns. All right, let's try some examples here, class. Number 1, what is the 30th term? So what do we know automatically? If it's 30th term, we know n equals 30 in a sequence where it starts with a, so a equals 27. And we have to see, hey, what's the patterning going on? What happens each time here, ladies and gentlemen? Okay? And hopefully you notice the pattern that you're subtracting 5. Okay? Again, if you're not sure, d in this case would equal 12, subtract 17, which equals negative 5. Or that still equals 17, subtract 22, which equals negative 5. Okay? So in this case, we've now developed that d equals negative 5, and all we have to do is sub it into our general term. Okay? So we're going to start with t at n equals a plus n minus 1 times D. Sub in our information. So T at 30 equals A, which is 27, plus 30 minus 1 times negative 5. So we have 27 plus 29 times negative 5. Okay, you can plug that all in your calculator, ladies and gentlemen, and you're going to get negative 118. Now, I want you to pause and make sure this makes sense. When we get to 30 terms, should it be negative? Because we're already at 12 and we know we're getting 5 less each time. Yes, it does make sure that it does make sense to have a negative number. So check your answers for reasonability there to make sure that it's reasonable. Okay, example 2. State the general term and the recursive formula for this following sequence. Okay, so just remember, guys, and tells us we got to do 2 different things here, right? So what do we know? First of all, we know A is what value, guys? A equals 3. We're trying to find out, hey, what's happening with our patterning? So we're noticing in each case we're adding 4, right? So that means our common difference is 4. Okay, and general term is what we're trying to find. So T at n equals question mark. So start with the general equation. I'm just going to write it out one more time. So you got it. Oopsie, my fault. There we go. I wish I could pause and rewind, but no. You can see my errors. There we go. Okay, sub in what we know. We know A equals 3. We don't know what n is, so it's going to be n minus 1 times d, which is 4. So let's simplify that. So it's going to be 3 plus 4n minus 4. Okay, I'm not sure why I have a bracket on the end here. Sorry. Okay, and collecting like terms, ladies and gentlemen, you're going to have that it's 4n minus 1. So that's the general term. That's what they're looking for right there. Okay, now it says to do what's called the recursive formula. Okay, so what do we know recursive is? It depends on, hey, what's in front of that term. So you take t at n, subtract 1, and then you add d. Okay, so you leave the t at n, subtract 1, and add 4. What does that basically say? It doesn't matter whatever term's in front, you add 4, and you're going to get this next successive or recursive term. All right. We can use a sequence by considering the term t at n as a coordinate and the term number n as the x-coordinate. Okay? So what we're going to do is do a little graph here. So we've got, just think of this being on your x-axis and this being your y-axis. I think they're labeled, yep, good here. Okay, so if I take a look at what we've done so far, okay, and I give you this example, which is an example 2. So in example 2, my term number 1, so my first term number, the value is up here, guys. See where I'm starring up here? The first value was 3. My second term number is 7. My third term number, hopefully you can follow that patterning now. The third term number was 11. And your fourth term number was 15. Okay? Everybody okay with that? All right, so to set up our graph, n is our term number, so let's just space them out each. 1, 2, 3, 4. So go every other, or you can go 3, you'll fit it in there. And then we got to take a look. Within our range of what we're graphing, I'm going to start at 0, and I got to end up at 16. So I will make each one worth 1. So there's 2, 4, 6, 8, 10, 12, 14, 16. Okay, so now we can plot these, ladies and gentlemen. Okay, so we're going to plot 1 and 3. Okay, we're going to plot 2 and 7. We're going to plot 3 and 11. And we're going to plot 4 and 15. Okay. Now, normally, ladies and gentlemen, I see people taking a ruler out and drawing a straight line. However, what you have to remember, guys, is that this is discrete data. Okay, and because it's discrete data, we do not join them. Okay, therefore no solid line. If you need to, you can use a dashed line. And the understanding of this, folks, is when you're doing a sequence, right? We've got term 1, 2, 3, 4. Can we have, the question is, can we have a 2.3 term number? No, it's either 2 or 3. So that's why we call it discrete, because you can only have a second term or a third term number. Okay, that's what makes it discrete. Okay. Okay. The reason why is x belongs to a set of natural numbers. Okay? All right, so you can either leave your graph like that, or I'll just throw in a dashed line because I have the ability to do that. Okay, but not a solid line, okay, guys? All right, notice here, folks, that what type of relationship are we connecting this to? It is a linear relationship. Okay, so the trend is linear. However, this is discrete data. All right, that's why you don't have a solid line. All right, moving on. Okay, we're going to just talk about a continuous versus a discrete function in the next page. All right, a continuous function has a domain where x belongs to a set of real numbers. Okay, there are no gaps and spaces between the points. Okay, so for example, y equals sine x. Just remember from sinusoidals, you start at your axis, go up, go down, etc., right? Okay, it's smooth and it's curved. Okay, remember, we draw a solid line. Okay, sequences are, as I've been describing, guys, discrete functions. The domain is a set of natural numbers. So you're going to say that n belongs to a set of natural numbers because n is going to be your term number. And that's what you're going to be graphing. And the range in this case is just the actual data points. So we had 3, 5, 11, 15, ... because it keeps going, right? All right. So we can use function notation for discrete functions as well. Just remember, ladies and gentlemen, that the graph below was linear, right? So if I flip back there, we could calculate the slope. So the slope of that, ladies and gentlemen, again, is rise over run. Okay? And we could just flip back for a second. Flip. Okay? So how much did we rise in between each point? Okay? Hopefully you counted 4 and you run 1. Okay? So it's going to be 4 over 1, which equals 4. And hey, in the linear model, that is the common difference. Okay? And notice also, guys, if we took a look at our graph, the y-intercept equals -1. And where does that come from? That's taking our first value of a and subtracting d. Okay, because that's at term 0, right? Term 0, which means that n equals 0. Okay, we've got to subtract 1 more. Okay, so the last thing we can do to get it in function notation is saying f at n, which is really your y, equals 4n minus 1. How does that relate, guys? That's your old y equals mx plus b. We just have it in function notation. So in general, ladies and gentlemen, to put it into function notation, you're going to use this formula. So f at n equals dn plus a minus d. Okay? And remember, d is the slope, which is the common difference, and a minus d is your y-intercept. All right, come see me if you have trouble with that one. I think it's an easy concept. Just got to remember what to do for the y-intercept. All right, last question. This is a tricky one, and I would say make sure you know how to do this for your test. Okay. What's tricky about this, folks, is it says to determine the number of terms in the sequence. So what are we actually trying to find? We need to try to find what n equals. This is not normal, okay? Also notice that we have an n value here, guys. It ends, okay? All right. A couple things we can figure out. We can figure out our start value, which is a. So a equals 9. We can also see, hey, what's happening in our sequence. So what's happening each time? Hopefully you realize that we're adding 7, right? So that tells me that d equals 7. So when I take a look at my formula, I've got t at n equals a plus n minus 1 to the d. Sub in what we know, which is a and d. So we got t at n equals a, which is 9, plus n minus 1 times 7. Okay, simplifying this out, ladies and gentlemen, we notice that we have here 9 plus 7n minus 7, which equals 7n plus 2. Okay, so far so good. However, can we find out what n is? Not yet, but there's a key here, guys, in that this is given. Okay? We don't know how many terms it is, but that's the end. And if it's the end, then in the general term, the t at n equals 100. So substitute that in. You're wondering why I didn't put that in. We'll substitute that in. Now we've got enough information that we can get the n isolated and solve for n. So bringing the 2 over, you're going to have 98 equals 7n. To get n by itself, divide both sides by 7. So you're going to get that n equals 14. Okay, so therefore, there are 14 terms. Great. So hopefully that was good for you guys, a good introduction to our last unit. Hopefully you noticed when you turned to your textbook on page 424 that, wow, we're almost at the end of this textbook, and you're right. Okay, this is our last official unit, and then we'll be doing review before your exam. All right, so here we go, guys. Page 424, numbers 8. I want you to add part 4, which is function notation, and then do 9 to 11 and give 15 a try. Have a great day, guys, and come and see me if you need some help. See ya.